Hello. Now we're going to talk about surface area, or rather, we could call this surfaces of a revolution. And the goal here, we want to find a double integral for calculating the area of a curved surface S based on the parameterization R in terms of U and V. And of course, those U values are going to be between A and B bounds. The V values will be between C and D bounds. So let's begin thinking about how to derive this. In order for us to do this, we need this S surface to be smooth. And the definition of smoothness involves these two partial derivatives. So taking the partial of R with respect to U and R with respect to V. And this looks pretty typical to what you might expect it to look like. And we can use the two different notations, R sub U or partial R with respect to U, either way. And so we would just take the partial derivative of each component in R sub U with respect to U and in R sub V with respect to V. So this word smooth being important to the definition, if we have a parametrized surface, R in terms of U and V, and we can say it is smooth if the partial of R with respect to U and the partial of V with respect to U are both continuous, and then this cross product, R partial U cross R partial V, is not zero anywhere on the inside of the domain. The concept of this cross product never being zero, being part of this definition of smoothness, this means that both of these partial derivatives are also non-zero and that they are never on the same line. So they can always determine a plane which is tangent to the surface. So let's visualize what we're going to be doing here. Essentially, we're going to take my UV plane, and somewhere in my UV plane, I have a region. We'll call that R. And then somewhere on that region, it would likely be smaller than what I've drawn here, but I want to write inside of it. We would have some area, delta A sub UV. So we have a rectangular area. And the idea is, again, thinking about that Riemann sum definition, is I can divide this region into all these little rectangular areas, and I can find the area of each region and sum them up. Again, thinking about that delta A becoming increasingly small. All right, inside this region, I'm going to place a point, P naught. And P naught is some U naught, V naught value. And what we can see is that we have a V naught and a U naught here on my U and V axes. And then essentially the idea is we've got some other distance that is plus some delta U, or vertically we would have some distance which might be plus some delta V. So those are creating some bounds on that small area. And the idea is we're going to apply this parameterization and map this area onto a surface. So here we're in our XYZ plane, and potentially we've got some curved surface here. It doesn't have to be curved, but I'm going to visualize it that way because it could be. So we've got this bound. This is going to be my U, representing my curve 1. So drawing this, mapping this line up here into my plane or my surface, we'll call that C sub 1 or path 1, which would be U equals U naught, and then further away from the y-axis, we will end up with U equals U sub naught plus some delta U value. So those are my these two bounds on that rectangular area mapped onto my surface. Similarly with my V values over here, I've got curve 2, which is V equals V naught, and then further away we would have V equals V naught plus delta V. So this, because this could be, curved, this is what we're going to call our patch element. So that's my patch element of the area. And we are going to refer to that as delta sigma, or rather delta sigma u sub v. So this sigma variable is what we use to represent the surface area of this patch, which has been mapped by the parametrization of R onto the surface. So we've got our R region in the UV plane. A delta A represents the area of a rectangle, which we map to that surface and creates this surface area patch element. So that delta A sub UV corresponds to delta sigma UV. So going back and considering the point on the corner here, and it doesn't have to be on the corner, I've just drawn it on the corner for convenience, but P naught being a point somewhere in that area. So if P naught is in that area, then the tangent vectors at P naught are going to be each of those partial derivatives evaluated at that point. So we have partial of R with respect to U at the point and partial of R with respect to V. And both of these partial derivatives are going to be tangent to the surface at C sub 1 and C sub 2. So again, thinking about what we're looking at here, we're mapping that point up onto this surface, and we have these two partial derivative or tangent vectors, and they're intersecting at P naught on the surface. And we want to know the area of this patch, sigma sub UV. And so that would be summing all of these rectangles that we've mapped up onto this surface, would be summing all of those different surface areas. So just repeating again, we have all these different rectangles in the region, and we mapped them all up to create different patches or sigma sub UV surface areas on my surface. And then basically we just want to sum all of these sigma, these little patch areas. So I'm going to pull in the book picture because I think it's a little easier to look at, but I think there's something wrong with the notation. So this is basically the same thing that I drew. It's just a little cleaner. We have our region with an area, and again, we have lots of rectangular areas on that region becoming increasingly small, and then we sum them all like a Riemann sum. So U naught, and then some other U value, which is delta U away, V naught, and then some other V value, and we're taking them and mapping them by the parametrization up onto this surface. So that point, P, is up here in this corner, closest to the origin. And as I was saying about the notation, I think all of these weird little X boxes represent equal signs. Okay, so we have U and U, V and V. The goal of what we're going to do here is we're going to approximate sigma sub UV using vectors. And that means we're approximating an area, and area using vectors is the magnitude of the cross product. Okay, so again, we're going to approximate this sigma surface area using vectors, and in order to do that, we'll be finding the magnitude of the cross product of these vectors. So let's kind of derive this. So if we think about delta of u sub v, that is going to be roughly the magnitude of the scalar delta u, that small horizontal distance, multiplied by the vector partial r with respect to u, crossed with delta v, multiplied with partial of r with respect to v. Now, since these are both scalars, or constants, we can pull them out. And so that leaves us with the vector r sub u cross r sub v, delta u, delta v. And so this represents the area. Summing all of these up, the area S as a whole is going to be approximately the sum of all of these cross products, delta U, delta V. This is the basic idea of the Riemann sum for surface area. And of course, we want to remember that we're going to be summing over some U values between A and B, as well as the V values, which will fall between C and D as our bounds. So this sum we found here, we're going to let that be d sigma. D sigma is going to be equal to the cross product of the vector r partial u crossed with the vector r partial v, du, dv. Then the area of the smooth surface S, where S is given by the parametrization r of uv, that is going to be that area equals the double integral over r of r partial u crossed with r partial v dA. And then again, thinking about that dA is just du dv. That's the area of my UV region. So we'll say the integral from C to D, the integral from A to B of r sub u cross r sub v, and this would be du dv. So both of these integrals mean the same thing, and you'll notice that this integrand we have here with the du dv, we could denote that as d sigma. So sometimes you may see this written as the double integral of the surface d sigma. So all three of these integrals mean the same thing, and this is how we find the surface area. So let's look at an example. In this example, we're going to find the surface area of this cone frustum, which lies between the planes z equals 1 and z equals 4/3. Well, the first thing we need to do is parametrize this function. And this is very similar to an example we did in the video before this, where we were parametrizing a cone frustum. What we're going to do here is I'm going to let my x, or my f function, be equal to r cosine theta. I'm going to let y, my g function, be r sine theta. So just using polar coordinates to express r and y. And then in polar, we know that r is equal to the square root of the sum of x squared plus y squared. So we can say that z is going to be equal to r over 3. So that means my r of uv, or in this case, r of r theta, we have r cosine theta I plus r sine theta j plus r over 3k. Now, in order to find surface area, remember we need partial of r with respect to each variable, in this case r and theta. So r partial r is going to be cosine theta I plus sine theta j plus 1/3 k. And then r partial theta is going to be negative r sine theta I plus r cosine theta j plus 0k. So we need the cross product of these two vectors, and then we need to find the magnitude. I'm going to find the cross product first. R sub r cross r sub theta. That's going to be the determinant set up by this matrix. I'm going to write I, J, and K up here. So I've got cosine theta, sine theta, and 1/3, and then negative r sine theta, r cosine theta, and 0, which looks like this. So when we are dealing with the I term, we're going to have 0 times 1/3. R cosine theta, we'll be subtracting that, so it's negative. Then remember, we always put a minus in front of the j term. So leaving those out, cosine times 0 gives us 0 minus a negative 1/3 r sine theta, that's positive. And then k, we'll get r cosine theta squared plus r sine theta squared, because it's going to be minus a negative. So this can simplify just a little. So the only thing that really simplified here was we used a Pythagorean identity. That k coefficient function became r. So now we need the magnitude of this cross product. So taking each component, squaring it, and then the sum, we're going to simplify a little bit. That's going to give us 1/9 r squared cosine squared theta, 1/9 r squared sine squared theta, and then plus this r squared, which looks like this. And we have a Pythagorean identity, which simplifies out, which leaves me with the square root of r squared plus 9 plus r squared, which is 10/9 r squared. If we think about that as 1/9 and 9/9, we've got 10/9. And the magnitude of this cross product simplifies to root 10 over 3 times r. That r is not under the radical anymore. At this point, we've found that cross product, the magnitude of the cross product, that's essential to our definition for surface area. So let's set this up. So this is what the integral will look like that we need to set up, and we need to determine what our r values and our theta values will be between. Now, since this is a cone, it's going to be a complete circle. We know that theta is going to go from 0 to 2 pi. But what is r going to be? Now, keep in mind, part of our parametrization was that z is equal to r over 3. And we were given this was bounded between the planes z equals 1 and z equals 4/3. So that means if I plug in 1 for z, I will get r equals 3. And if I plug in 4/3 for z, we get that r equals 4. So setting this up, this is going to be the integral from 0 to 2 pi for theta, 3 to 4 for r. I have the square root of 10 over 3 r dr d theta. So once we have it set up, this is a very simple integration. Encourage you to pause, make sure you can work it out. It's always good to get that practice. I'm going to pause and work it out myself. With a quick, easy integration, we get that the surface area of this cone frustum located between these two z-planes, z equals 1 and z equals 4/3, is the value 7 root 10 times pi, all divided by 3. And that's how we set up these surface area examples. So I hope that helps. Good luck, and let me know if you have any questions.